Hello everyone, welcome to another video of class 10 general mathematics, and today we are going to do exercise 1.3, a very important exercise because this type of sums are really important in the exam and you are almost guaranteed to get one of these sums in your HSLC. So we have to prove irrational numbers. Some numbers you have to prove that they are irrational, and these are the square roots of some of the numbers. For example, any prime number, or even if it is not prime, it is not a perfect square. So the square root of any non-perfect square will be a irrational number. So we have to prove this. So let's see how to prove this, and we are going to start off directly from the exercise because the pattern of proving these sums are same for all of them. So we are just going to see what is the pattern by taking one of the sums from the exercise. So the first one, question number 1, is we have to prove that root 5 is an irrational number. So how do we do this? So in order to prove root 5 as irrational, we start it off in a bit different way. And the difference is that generally whenever we prove something, we follow our pattern, our regular pattern. We start off from one of the LHS or RHS and we move to the other part. This time we are going to take a different approach, and what we are going to write, the first line itself is the different approach. So we are going to assume, so let us assume root 5 is a rational number. This is the first line we are going to write, that let us assume root 5 is a rational number. So once we have assumed that root 5 is a rational number, therefore we can write root 5 is equal to p by q. Of course, because rational numbers can be expressed in the form of p by q, where p and q are integers and q is not equal to 0. Along with that, we can also assume that p and q are in the simplest form. That means p and q are co-prime numbers. For example, by co-prime, I hope you know what is co-prime number. A co-prime number means two or more numbers which do not have any common factor other than 1. For example, 3 and 7. 3 and 7 are co-prime numbers because there is no common factor between 3 and 7 other than 1. Okay, so 3 and 7 are co-prime. So we'll also assume that p and q are co-prime. So co-prime means there will be no common factors other than 1. Remember this because this is the most important part of this proof. The most important part, p and q are co-prime. Okay, so root 5 is equal to p by q. We can write it like this. What we can do next is we can write p is equal to root over 5 into q. Right? We can do square of both sides, p square, and it will be root 5q whole square. This is the squaring both sides. And what we get is p square is equal to 5q square. Done? Simple. Now, here p square is equal to 5q square means 5 is a factor of p square. So therefore 5 is a factor of p square, right? Now if 5 is a factor of p square, that is 5 is a factor of p. Okay, now this is a theorem actually. This theorem states that if a divides b square, then a also divides b. Remember this. For example, let us take one simple example. Suppose 4 divides means is a factor. It will completely divide. The remainder will be 0. So suppose 4 divides 8 square. 8 square is 64, right? So 4 is obviously will divide 64. So 64 is divisible by 4. Now since 4 divides a square, we also know that 4 divides 8. 8 is divisible by 4. Right? So that means if a number divides the square of some number, that number will also divide that particular number. So here 5 is a factor of p square. So that means 5 will also be a factor of p. Okay? Done. We'll keep it to this. Now since 5 is a factor of p, thus what we can write, the next step we can write is p is equal to 5 into anything. Suppose r. P is equal to 5r. We can write it like this. P is equal to 5r. Where r is any integer. Since 5 is a factor. So since 5 is a factor of p, therefore p will be equal to 5 into something. Obviously, since 5 is a factor. So 5 multiplied by something will give us p. Again, if we do the square of both sides, we get p square is equal to 25r square. Right? I am continuing this part here. Okay, p square is equal to 25 r square. Now what is the value of p? We will take it as number 1. P square can be written as 5q square. So in place of p square, we will write 5q square is equal to 25 r square from 1. Okay. Now q square will be equal to, if we do a side change, we are going to get 5. So it is 5. That means q square is equal to 5r square. Now here comes the interesting part. So since q square is equal to 5 into r square, therefore 5 is a factor of q square, right? 5 is a factor of q square. Since 5 is a factor of q square, that is 5 is a factor of q also, using this theorem. Now you see the interesting part. What we had assumed that p and q are co-prime means there will be no common factor. But here we see 5 is a factor of p and here 5 is also a factor of q. That means 5 is the common factor of p and q. But we had assumed that they are co-prime means there will be no common factors. So since our proof shows that they are not co-prime, therefore our assumption was wrong. If this assumption is wrong, that means our assumption that they are rational numbers is also wrong. That means root 5 will not be rational, it will be irrational. And that's how you prove that root 5 is an irrational number, by taking a reverse technology, or not technology, a reverse method. You go in a different direction, the opposite direction. So what we will write, how should we write this part? Let's see. So therefore 5 is a common factor of p and q, but we had assumed that p and q are co-prime. Therefore our assumption is wrong, and hence our previous assumption that root 5 is rational is also wrong. Therefore root 5 is an irrational number. Hence we have proved the sum. So that's how we prove these type of sums, where we have to prove that some numbers are rational whereas some are, these root 5, root 6, root 2, root 3. So whatever you get, in place of root 5, if you get root 2, you can do it in the same way. And in place of 5 being the common factor, you will find 2 is the common factor for root 2. For root 3, you will get 3 as the common factor, and likewise. Okay. So that's how we do it. Let's try question number 2, where it may seem complex, but it is actually easier. So we have to prove that 3 plus 2 root 5 is irrational. So again we will assume, so let us assume that 3 plus 2 root 5 is rational. So therefore obviously 3 plus 2 root 5 will be equal to p by q, as we know. P and q are integers and q is not equal to 0, as usual, that whatever we write. From here what we will do, we will change the sign of everything and we will find the value of root 5. Okay, so it will be 2 root 5 equal to p by q minus 3. So therefore root 5 will be, if we take the LCM here, it will be q, it is p minus 3q, and side change of 2 will bring it to the denominator, it will become twice q. So root 5 is equal to p minus 3q by twice q. So from here what we can write? So since p and q are integers, p minus 3q by 2q will be rational, right? Since p and q are integers, obviously this value p minus 3q by 2q will be a rational number. But as we have seen previously, root 5 is an irrational number. That's what we know. That's what we have known from the previous sums. So even if you don't do the previous sum during the exam, this thing will be taken as a fact. Okay, we will consider this as a fact when we have this type of complex numbers. Okay, this is not a complex number, means this type of numbers which include both the rational part and the irrational part. These sort of numbers, whenever you get combination of these types of numbers and we have to prove that they are irrational, Here we will take it as a fact that root 2, root 3, root 5, root 7, these numbers are irrational. So but root 5 is a rational number, that is what we know. So as root 5 is irrational, therefore our assumption was wrong, right? We know we have considered this to be rational, and that's why we got p by q, and ultimately we got root 5 to be a rational number, but root 5 is a irrational number, therefore our assumption was wrong, and hence 3 plus 2 root 5 is irrational. Again we have proved it. See, although this seemed complex, it is actually easier and much simpler sum. Done. Let us do one more part, and that is question number 3. And why I am doing question number 3? Because question number 3 Roman 1 is actually a bit you need to do a simple step. So it is 1 by root 2, and to prove that this is irrational. So before we start, always remember to rationalize the denominator. So the denominator is not rational, right? So we will rationalize the denominator. How do we do this? We will multiply root 2 on both numerator and denominator. As a result, we get root 2 by root 2 square, and it becomes root 2 by 2. Now we will continue in the same process. That let us assume root 2 by 2 is rational. Accordingly, we will get root 2 by 2 is equal to p by q, and we will write whatever we need to write. Then we will get root 2 is equal to twice p by q. Here p and q are integers. Therefore, twice p by q is rational. Same process. But we know that root 2 is irrational, but root 2 is irrational. Therefore, our assumption was wrong. Therefore, 1 by root 2 is an irrational number. Hence proved. See, it was easy. So this exercise is over. 1.3, a very important exercise. In a small video, we have combined the whole and crunched it into a single video. I hope you have understood. If you have any confusion, make sure you ask me in the comment section, or you can ask me directly. And I hope you enjoyed the video. So thank you everyone for watching, and until next time, cheers.